Black holes could be the source of dark energy. An exciting new study has shown the possibility that supermassive black holes are the origin of dark energy, one of the most mysterious entities in the universe. According to our most successful cosmological model, 68% of the universe is made of dark energy, while ordinary matter like stars and galaxies make up just 5%. Despite their similar names, dark energy and dark matter are vastly different entities, with their composition remaining a mystery to scientists. Whatever comprises dark energy, it's important to understand it because the fate of the entire universe rests upon it. But the crisis is that, although it's an exciting thought, not everyone is open to it. So how did astronomers come up with this idea? What did they observe in the universe that led them to this hypothesis? Finally, and most importantly, why is this idea so controversial? The first clue of the connection between dark energy and black holes did not come from either of the two. Instead, it came from elliptical galaxies. These galaxies have an ellipsoidal shape and lack the spiral arms characteristic of their spiral counterparts. Typically composed of an older, redder population of stars, ellipticals are thought to be in the final stages of galaxy evolution. They're likely formed through the collisions and mergers of spiral galaxies or the gravitational collapse of interstellar gas clouds. In the future, when the Milky Way crashes into the Andromeda Galaxy, it is speculated that their spiral structures will morph to become an elliptical galaxy. Despite their different origins, all observed elliptical galaxies share a common feature: a lack of gas and dust to support typical star formation. This deficiency is believed to be due to a supermassive black hole in the galaxy's center, which accretes mass from the surrounding stars, limiting their growth and eventually exhausting the fuel needed for star formation. As a result, the black hole eventually stops accreting, leading to a galaxy devoid of new stars. This connection between supermassive black holes and the end of star formation in elliptical galaxies is crucial in understanding the relationship between black holes and dark energy. Elliptical galaxies are generally considered to be stable in their shape and mass once they are fully formed. However, recent studies have shown that some ellipticals exhibit an increase in mass over time, prompting astrophysicist Duncan Farah and his colleagues to investigate the evolution of these galaxies further. Their study focused on elliptical galaxies of varying ages, each hosting supermassive black holes, millions or billions of times more massive than the Sun at their center. When plotting the galaxies according to their black hole mass and stellar mass, the team noticed a puzzling trend. In this graph, red dots are the nearby old ellipticals, blue dots denote ellipticals from 6 billion years ago, and orange dots represent young ellipticals from the first 2 to 3 billion years of the universe. So basically, what astronomers have done is that they have compared very young elliptical galaxies that emerged in the early universe to the old ones that we see in the local universe. By comparing them, astronomers can study how young galaxies evolve into the ones we see today. However, they found a significant offset in the correlation between the mass of the stars in the galaxy and the mass of the supermassive black hole. Specifically, black holes at the center of low redshift ellipticals had a mass 7 to 20 times greater than what was predicted by studying high redshift galaxies. This unexpected finding challenges our current understanding of galaxy evolution. If ellipticals are supposed to be stable once fully formed, where's this extra mass coming from? The answer to this question could be dark energy. However, To understand how dark energy might be connected to the excess mass of black holes and elliptical galaxies, we must explore two crucial concepts: vacuum energy and cosmological coupling. Vacuum energy refers to the energy that permeates all of space-time. This energy arises due to the constant popping in and out of virtual particles that occurs within the confines of the energy-time uncertainty principle. Despite the apparent randomness of this process, it is thought that the total energy of vacuum fluctuations is a relatively constant value. As the universe expands, the space or vacuum inside it also expands, increasing the total amount of vacuum energy. The new model suggests that black holes have an interior vacuum energy, which expands along with the universe, thereby increasing the black hole's energy. And according to Einstein's mass-energy equivalence, as the black hole's energy increases, its mass must also increase. But to conserve the total energy of the universe, the black hole exerts a negative pressure outwards. This negative pressure causes everything around the black hole to be pushed away from it, accelerating the expansion of the universe. The negative pressure exerted by the black hole is the exact nature of dark energy, whose equation of state suggests that the energy density of dark energy is equivalent to the negative pressure it exerts. This means that dark energy and black holes are interconnected or cosmologically coupled. The cosmological coupling can be expressed by a simple equation. Here, m is the black hole's mass, and a is the scale factor that describes the universe's expansion. So AI is the initial scale factor of the universe when coupling starts, and m of AI is the initial mass of the black hole. As the universe expands and reaches a scale factor of a, its mass changes to m of a. Finally, k is the dependency of the final mass on the expansion of the universe. It's called the cosmological coupling strength. Their hypothesis says that if there is no cosmological coupling in the universe, k is 0, and the initial and final mass of the black hole is the same as the universe evolves. But if there is cosmological coupling, then k should equal 3, and hence, the black hole's mass after the universe's expansion is greater than the initial black hole mass. This is the gist of the intriguing idea behind the study they conducted. The idea that black holes could be a source of dark energy is fascinating, but is there any evidence in its favor? How did they confirm this idea when the interior of a black hole is still unknown? To address this question, researchers turned to low redshift elliptical galaxies, for which they had previously found an increase in the mass of the supermassive black hole. They compared the masses of these black holes with those of young elliptical galaxies using the equation of cosmological coupling, which describes the relationship between the expansion rate of the universe and the vacuum energy density. Surprisingly, the value of k, representing the coupling parameter, was found to be 3.11. The probability of these galaxies having a k value of 0 was negligible, meaning the chances of the black holes in these galaxies not being cosmologically coupled with the universe were almost 0. Further analysis showed that black holes could account for the total amount of dark energy in the universe, which is approximately 68%. This result also explains the coincidence problem, which questions why the universe recently became dark energy dominated. This study suggests that a complete evolution of galaxies is necessary for black holes to contribute as a dark energy species and dominate, thereby accelerating the expansion of the universe. As exciting as it may sound, the proposed idea has some limitations that must be acknowledged. These are because of a few loopholes in the hypothesis. Firstly, the researchers compared galaxies from different eras of the universe due to the impossibility of studying a single galaxy throughout its entire lifespan. However, this comparison assumes that the evolution and growth paths of galaxies were similar across different eras, which may not be the case. Secondly, They have boldly assumed that black holes exert negative pressure, a characteristic of dark energy. Finally, the study only considers singularity-free black holes, which are not fully established in scientific literature. However, we must not dismiss theoretical ideas such as this one outright. Some of the most groundbreaking discoveries in physics and astronomy started out as theoretical predictions. For instance, Wolfgang Pauli's prediction of neutrinos in the 1930s led to their discovery in 1956. Similarly, Neptune, the Higgs boson, and gravitational waves were all discovered through theoretical predictions. So we must remain speculative and find evidence to see if the idea